Alright, in this video we're going to take a look at how to do acid-base titration calculations, mostly using unit multipliers. This is for grade 12 chemistry, both regular and advanced placement. So a titration, we've done this in the lab, but it's a volumetric analytical technique involving reacting two substances that are dissolved in solution. One of the substances is placed in a burette, and burette can be spelled either with one T or double TE, as you see in the picture. In our lab, we filled the burette with sodium hydroxide when we did this, so it says here the burette is filled with a base, but it really is kind of arbitrary whether you put the base in the burette or the acid in the burette. In any case, whatever's in the burette is called the titrant, and then it's being added quantitatively, in other words, knowing the volume exactly using these graduations on the burette, to a flask, and the flask contains, in this case, an acid, and that flask contents is referred to as the analyte. So the titrant in the burette is reacting with the analyte in the flask. Now, during the titration, we know that one substance, as we said, contains an acid, the other is a base. The equivalence point is the point in the titration where the two reactants have exactly neutralized each other in the flask. So the mole ratio in the flask at that point is exactly the same as the stoichiometry in the balanced neutralization reaction. So if they react in a 1-to-1 ratio, then at the equivalence point you'd have equal moles of acid and base in the flask. If it's a 2-to-1 ratio, then one of them is going to be twice as many as the other in the flask in terms of mole ratio. The products of neutralization are almost always going to simply be a salt of some type and water. A common misconception is that neutralization means neutral. It does not. Since there's a salt produced in the reaction, the pH at the equivalence point is determined by the salt being produced. Some salts, we know, produce neutral solutions, so sometimes the pH at the equivalence point is neutral, but often salts produced will create basic equivalence points and sometimes even acidic equivalence points. So the pH is not necessarily neutral at the equivalence point. Acid-base reactions are kind of boring to watch because usually the titrant in the burette looks like clear colorless liquid, looks like water, and the analyte looks like water, and when the reaction happens it's like you're adding water to water, so the reaction's kind of boring. In fact, not only is it boring, that poses a problem because we're supposed to stop titrating when we've got exactly the right mole ratio in the flask. So how do we do that if you can't see the reaction? The answer is to add an indicator, an acid-base indicator. An indicator is itself a weak acid that changes color at a particular pH. If we know the salt being produced in the titration, we can predict what the pH will be close to at the equivalence point, and then we choose an indicator which changes color close to that pH value. So when you're doing the titration, you stop the titration at what's called the end point, and that's where the color of your indicator changes. So for example, we used phenolphthalein as an indicator in our titrations. In an acid solution like we see up here, the phenolphthalein was colorless, but then when we added the base, the pH rose and eventually the solution turned pink inside the flask. That pink color, permanent pink color, told us to stop titrating. So that means we reached the end point of the titration. Theoretically, your end point, where you actually stop because there's a color change, should be the same as your equivalence point, where you were supposed to stop because the acid and base were exactly neutralized. If you choose a poor indicator, or if you're just not very good at titrating, you may add more or less titrant and stop titrating at that point. So sometimes because of errors, your end point is not the same as an equivalence point. There are several purposes to titrations. One common purpose is to standardize a solution. If you have an acid or base solution whose concentration you don't know, you would standardize it. In other words, determine the concentration exactly. Another purpose would be to find the molar mass of an unknown acid or base. A third purpose might be to do maybe a commercial analysis and find the percent by mass of an acid or base in some kind of product, like a medication, for example. So with that little background, let's jump in and take a look at some standard titration questions. We'll look at 4 titration problems. If you're using this as review, then pause the video and try the problems yourself. If it's your first time seeing titration problems, then maybe do the first 1 or 2 with me, pause the video just to copy it down as I'm going, and then try the problems yourself for the last couple. So the first problem, standardizing a solution of sodium hydroxide. This reflects what we did in our experiment in the lab. A student dissolved 0.601 grams of potassium hydrogen phthalate, we'll call that KHP, the P there is for phthalate, not phosphorus, in about 25 mils of distilled water. The KHP, we know, is a weak monoprotic acid. It's got a molar mass of 204.2 grams per mole. Because it's monoprotic, we'll represent it as HA in a chemical equation. Phthalate is a rather complicated molecular formula, so we'll just use HA for simplicity. This sample of acid now required 22.37 milliliters of sodium hydroxide to reach the end point of the titration. Calculate what the concentration of the sodium hydroxide was. So the first thing you want to do in a titration problem is get the balanced chemical equation, because we're going to need the ratio in which these things react. So the acid was HA, a monoprotic acid, and the base is sodium hydroxide, NaOH. Those are my 2 reactants. You'll notice with some grade 11 chemistry eyes that this is a double replacement reaction. In grade 12 chemistry we'd call it a neutralization reaction, but it is a double replacement reaction. The H from the acid and the OH from the base combines to make the water that we mentioned earlier, and then the sodium and the A, the cation and the anion, will combine to make a salt, so NaA. So there's the equation. Now the reason we wanted that equation was to note here that there's a 1-to-1 ratio between the acid and the base. That's going to be a unit multiplier for us in just a moment. So now we're going to set up some unit multipliers to find the concentration of the base. And one of the hardest things for students when using unit multipliers is to decide what to start with. Well, one rule of thumb is to not start with a unit multiplier. Concentrations are unit multipliers, so we wouldn't start with that. A molar mass is a unit multiplier, right? This many grams for every 1 mole, that's a unit multiplier, so we wouldn't start with that. The mole ratio from the balanced equation is a unit multiplier. We won't start with that. So that leaves in this question 3 numbers. The mass of the acid, the volume of the base required to reach the endpoint, and then there's this 25 mils. I hope you realize that the 25 mils is a little bit of a distractor. The acid was dissolved in that, but it's really not important for the question. You might have used only 20 mils. You might have used 30 mils. If you've done a titration, you know that that volume in the flask initially is really not that important, so it's not going to be in our calculation. So one rule of thumb is to start with a number that you can do something with. So which of these 2 numbers could we do something with? Well, if I have the mass of acid, and I know it's molar mass, then I can convert mass to moles. So there we have a little bit of a path to take, so that dictates what I'm going to do. I'll take the 0.601 grams of acid, and when I set up my unit multipliers, I don't put numbers in the multipliers until the end, so I'm going to just focus on the units. I'll convert my grams of acid, grams of HA, into moles of acid, moles of HA, and that of course uses the molar mass. Now that I've got moles of acid, we could use the mole ratio from the balanced equation. We can convert the moles of acid into moles of sodium hydroxide. We notice how the units are canceling out as we go, so this feels like we're headed in the right direction. And now we're trying to find concentration of sodium hydroxide. We have the moles of sodium hydroxide. How do you go from moles to molarity? Well, the answer is you divide by the volume. So the volume here is 22.37 milliliters, so I'll just divide by the milliliters of sodium hydroxide. Since I'm just dividing, I'll just put a 1 on top as a placeholder. But we know that when you're using a volume in a concentration, it's not supposed to be milliliters, it's supposed to be liters. Some people would have converted the milliliters to liters and then just put liters here, but I'm going to just do that right here. I'll get rid of my milliliters and I'll convert to liters like that. So now if I look at my units, what's left, what's not canceled out, is moles per liter of the sodium hydroxide. So I'm pretty confident that I've set that up right. Moles per liter is my answer. So now let's put the numbers in the unit multipliers. 1 mole of the acid has a mass of 204.2 grams. That's my molar mass. From the balanced equation, 1 mole of the base requires 1 mole of the acid, or 1-to-1 ratio, and the volume was 22.37 milliliters of base, and I know there's 1,000 milliliters in 1 liter. That's just by definition. So grabbing a calculator and then rounding off our answer to 3 significant digits, right? There's 3 digits divided by 4 digits divided by 4 digits, so we're only going to keep 3 digits in the answer. We get 0.132 moles per liter, or 0.132 molarity if you prefer. Okay, so there's the concentration of the sodium hydroxide solution. Problem number 2, if you think you kind of understood what we just did there, you might pause the video and see if you can try this question on your own. We're going to take the standardized solution that we just determined in problem 1, and we're going to use it in a titration with an unknown solution of phosphoric acid. And right away I noticed something a little complicating here. The phosphoric acid is H3PO4, which means it's triprotic. So 3 hydrogens in that formula. That tells me the ratio in this equation is not going to be just 1-to-1. 10.00 mils of the acid was pipetted into a flask, probably with a volumetric pipette. That required 27.52 mils of the base for complete neutralization. Now the word complete here is important. Since let's begin writing a balanced equation. We're going to calculate the concentration of the acid solution. So the phosphoric acid, as we noted, is triprotic. It's going to react with my sodium hydroxide. Now, depending on the indicator we choose, we could actually have 3 different situations here. We could choose an indicator which changes color after just one of the H's here is neutralized, in which case we'd end up with 1 water molecule, and then NaH2PO4 would be the salt produced. That would be a 1-to-1 ratio. We could also neutralize 2 of the 3 hydrogens, or we could neutralize all 3, and the choice of indicator would tell us when to stop at each one of those situations. Because the question said complete neutralization, we're going to assume that that means all 3 hydrogens were neutralized in this reaction. So look what I'm going to do here. I'm going to start balancing my equation before I actually write the products out. That sounds a bit weird, but take a look at what I mean. The H's are going to combine with OH's to make water. Since there's 3 H's here and only 1 OH here, I'll put a 3 in front of sodium hydroxide so that now the H's and OH's are equal, 3 and 3. So now I'm going to neutralize all 3 H's. The 3 H's and the 3 OH's will give me not 1 water, but 3 water molecules. And now whatever's left is the formula of the salt that I'm going to produce. So 3 sodiums and 1 phosphate gives me Na3PO4. Right? So there's the complete neutralization reaction. And we can see there that the ratio is not a 1-to-1, it's a 1-to-3 ratio, the way I've written it here. Alright, so let's jump in and begin the unit multipliers. We're trying to find the concentration of the acid. So I'm not going to start with the volume of acid. I'm going to use that at the very end. I'm going to start with the volume of the base. I know its concentration from above, so if I start with the volume of base, I can go somewhere with it. So 27.52 milliliters of the base. Again, I didn't start with the concentration of the base because the concentration is a unit multiplier. the concentration is moles per liter. So what I'll do first is get rid of the milliliters and switch to liters of sodium hydroxide. And now I can use the concentration to get rid of the liters of sodium hydroxide and replace it with moles of sodium hydroxide. Now that I've got the moles of base, I can look at my balanced equation. And the moles of sodium hydroxide can be replaced with moles of the acid, the phosphoric acid. That's where our 3-to-1 ratio is going to come in. And then finally, we're trying to find the concentration of the acid. We have the moles. To go from moles to concentration, we divide by volume. The volume was given in milliliters, but we know it has to be in liters actually, so we'll just convert those milliliters to liters. Now let's see how these units all cancel. The milliliters of NaOH cancels, the liters of NaOH cancels, the moles of NaOH cancels, the moles of H3PO4 does not cancel. The milliliters does, so what's left, if I just put a 1 there as a placeholder, what the units that are left are, moles per liter, means I've got the right answer, the right setup in my unit multipliers, moles per liter of H3PO4. So now let's put our numbers in. 1 liter is 1,000 milliliters. This is my concentration of base, which was 0.132 moles per liter. The mole ratio was 1 mole of acid for every 3 moles of base. The volume of acid was 10.00 milliliters, and again there's 1,000 milliliters in a liter. Alright, so now grabbing a calculator and evaluating this, you might notice right up front that the thousands cancel out, so you can omit those if you want. But typing it in on the calculator, you'll see the final answer is 0.044. But if we want 3 significant digits here, 3 digits and 4 digits, so we'll add a 0 at the end to give us our 3 digits. So 0.0440 moles per liter is the concentration of the acid. The third problem is one where we're going to try to find a molar mass of an unknown acid. See if you can pause the video now and set this up yourself. So we've got 1.002 grams of a diprotic acid dissolved in about 25 mils of distilled water. It needs 37.14 mils of 0.1217 molar potassium hydroxide for neutralization, and again, complete neutralization. What is the molar mass of the acid? So with a balanced equation, we've got the acid H2A, and we notice it's diprotic, right? It's going to react with our KOH. Again, a double replacement reaction, and 2 H's will require 2 OH's for complete neutralization. So I'll put a 2 in front of the KOH. That will give me 2 water molecules, not 1. And whatever's left is the salt being produced. So 2 potassiums and then whatever this A stands for. So K2A is the formula of the salt being produced. So the key in the balanced equation is the ratio here. It's a 1:2 ratio. Now, where do we start? Well, we notice there's a mass of acid. We're trying to find the molar mass. Now, those two are related, so I'm probably going to use this at the end of the problem. Here's a volume and a concentration of base. So I'm going to start with my volume, right? The concentration will be a unit multiplier. Don't start with unit multipliers. So if I take my 37.14 milliliters of the base, KOH, you should know by now milliliters will be converted to liters of KOH. And now this molarity is actually moles per liter. So we can convert the liters into moles of KOH. And now we've got the balanced equation, mole ratio. Moles of KOH can be converted to moles of H2A. And then we're trying to find the molar mass. So actually, I'm going to stop there and just get moles of the acid. That's what I'm going to use my unit multipliers with. And then I'm going to go find the molar mass with a little formula that we know. Molar mass is equal to mass divided by moles. Think of the units for molar mass. It's grams per mole, which means take the mass, grams, and divide by the moles. So if I take the mass of the acid, 1.002 grams, that was up in the question, divide by the moles that I've got here, I'll get grams per mole, which is my molar mass that I'm looking for. So coming back to my unit multipliers, a liter has 1,000 milliliters. The concentration of the KOH was 0.1217 moles per liter, molarity. The balanced equation says 1 mole of the acid needs 2 moles of the base. And so grabbing a calculator and evaluating that, you'll find out that there's 0.002260. I'm keeping 4 significant digits here because there were 4 significant digits in the problem. So that's how many moles of acid there were. We divide the mass by that number of moles of acid, and we find out that the molar mass is 443.4 grams per mole. Again, keeping 4 significant digits in the answer. Alright, this leads us to the last problem. Again, I encourage you to pause the video and try the problem yourself. A student found that an aspirin tablet has a mass of 0.474 grams. The tablet, we know, contains not just aspirin, it has filler material like starch and things. The tablet contains monoprotic acetyl salicylic acid, ASA. That's the commonly known aspirin ingredient. After dissolving the tablet in some alcohol, because aspirin's got very limited solubility in water, she titrated that and found that it required 18.45 milliliters of 0.105 molar sodium hydroxide to reach the end point of the titration. What was the mass percent of the acetyl salicylic acid in the tablet? To get the mass percent, if we just think about that for a minute, the percent of the acid, we'll call it HA, in the tablet, it's going to equal the mass of the acid divided by the mass of the tablet times 100. Well, we know the mass of the tablet, so it's something divided by 0.474, divided by 0.474 grams. So all I need to do is find the mass of the aspirin that was in that tablet, and then I can get the mass percent. So how do we do that? Well, again, a balanced equation. The acid is monoprotic, so we'll call it HA. It reacts with our sodium hydroxide, NaOH, in a 1-to-1 ratio. We can already see that now. 1 H and 1 OH gives me 1 water, and then the sodium and the A give me a salt of some type. So the 1-to-1 ratio is what I want to notice here. I'm going to start with the volume of the base because I know its concentration. I can find the moles of base that way. So if I take the 18.45 milliliters of sodium hydroxide, convert milliliters into liters of sodium hydroxide, and then the liters into moles of sodium hydroxide, and then using the balanced equation now, the moles of the sodium hydroxide, convert that to moles of the aspirin, the acetyl salicylic acid, we'll just say HA. We want grams of acid. Well, we know its molar mass, 180.16, so we can get rid of moles of acid, and we can replace that with grams of acid. And now the problem is pretty much solved. 1 liter has 1,000 milliliters. This is the concentration, moles per liter of the base. It was 0.105 moles per liter. This is the ratio, acid to base, from the balanced equation, 1-to-1. And this is the grams per mole. This is the molar mass of the acid, which was 180.16 grams per mole. We're going to keep 3 significant digits in this answer. Turns out that there was, doing all this arithmetic on a calculator, 0.349 grams of acid in that tablet. Maybe it was a 350 milligram tablet. So if we take the mass of the acid, 0.349 grams, divide by the mass of the tablet and times by 100, we find out that this tablet is 73.6% aspirin. So there you have it. We've looked at several types of titration problems: standardizing a base, determining the concentration of an unknown acid solution, finding the molar mass of an acid, and then finding the mass percent of an acid in a tablet. So those are all commonly used applications for acid-base titrations, and we've used unit multipliers throughout to solve them. So I hope that helps. If you have any questions on this, please don't hesitate to make an appointment and see me outside of class time.